As we begin our journey into calculus, a question that we all should begin to wonder of is, can change really occur at an instant? And what do I mean by an instant? So let's say you're going down the highway at 40 miles per hour, right? And this is what your speedometer shows. But what does this 40 miles per hour really mean? Well, it means a rate of change, right? I'm changing by some amount over some interval. So I'm changing my distance over time. But if you recall, this is a change, right? And so can really change occur at an instant if I need two different quantities to compare, such as that, let's say 5 minutes ago, I was at 50 miles away from my destination, but now I'm only 30. I'll just initialize with M over 5 minutes. This is a rate of change because now I'm comparing a before and after almost over some interval of time. But this 40 miles per hour, how am I saying that this is my rate of change at an instant? Well, let's really think about this a little further and what's really going on here. So let's take a really simple example here where I have this graph that graphs t squared. Let's say I wanted to compare the rates of change between 1 and 3. So 3 corresponds with 10, my position being 10 at 3 seconds, and my position at 1 looks like to be 1, right? So I can write this rate of change as f of 3 minus an f of 1 over 3 minus 1, right? But let's say I start getting closer and closer, right? We know this is my rate of change, but if I start getting closer and closer, let's say I start getting really close and I'm at 2 now. So I can look at 2. 2 is about 4, right? So let's say we're going to take f of 2 minus f of 1, 2 minus 1. And let's not forget our goal here. Our goal here is to find the rate of change at x equals 1. And so 2 is getting a little closer. Well, how close can I really get? Well, I can get as close as, let's just say, here. I can just be a small difference away from my original value. So what does that small difference away look like? So I'm going to make some room here to explain that. So that small difference away, let's say I'm 0.1 away. So now I'm taking the rate of change at f of 1.1 minus f of 1, 1.1 minus 1. And that's really close. Like, that's a really small distance that we're comparing over a really small interval, right? 1.1 is like 0.1 second after. So you can see that's really close to an instant because you don't feel zero point 0.1 of a second, right? So, but how closer can we even get? That's the point here. What is an instant? I can get as close as saying 1.001, right? And now my difference is just 0.01. And we can, just for our sakes of calculus, we'll call this the rate of change at an instant, right? We're comparing two different like points and finding a rate of change. But at the same time, I want to introduce the concept of a secant line. So let's come back to our original right here, f of 3 over f of 1. If I take my point at 3 right here, and I take 1, I can draw a line between the two and call it a secant line, right? A secant line represents my average rate of change because I'm finding the change, a line between 2 points. And then if I take my line of 2, and if you notice, the rate of change at 1, we can draw a line ourselves too, right? Let's say I want to make this the line that represents the instant rate of change at 1. We're going to call this the tangent line. And if you realize, the closer and closer I get to my value, like realize how far away was the orange line compared to the purple, and now the green, which is my like instant rate of change almost, the tangent line. As I get closer and closer to my point, I'm better able to approximate this line, because if my next point was, say I was comparing with this, well, my line will approximately just overlap the tangent line that I'm trying to estimate. And so all this to say, what is the rate of change at an instant? Well, we really don't know. What we can do is really approximate it with 0.001 of a difference. But calculus gives us an even better tool. Let's say that, let's rewrite this with a different notation. I'm going to say, I'm going to let my change be 0.001 denoted by h. Now if I find my rate of change, let's match colors. So f of 1 plus h. So I'm just moving over by little h, and everything else stays the same. So I am left with that, which is basically the same as keeping h in the denominator. And here's h in the denominator, right? If h is equal to 0.01, what if this is able to keep me really, really close? But what if I was to reduce this? I can make this 0.0001, and now my difference is even smaller, 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 smaller. Like I am basically touching my original point. And that's what your speedometer essentially does behind the scenes. You may be driving on the highway, it'll take a point here. And immediately after it takes another point and shows you that. Takes another point, shows you that. Takes another point, shows you that. It's just continuously taking those points and basically telling you the slope of your tangent line, the change, right? And calculus just makes it super easy. Calculus tells us that, or at least it gives us a tool that lets us take this h to almost zero. What if we could touch zero? Well, first of all, if I was to just make the change zero, right? Let's say I make h equals 0, then I would end up with 0 over 0. So we really can't say 0, because that would defeat the whole point of our whole lecture. Or rather, calculus says, what if I let you go to 0? What if I let you approach 0 as close as possible? And that's what we're going to call limit notation. We're going to expand on this, but that's the whole idea of it. And then I'll give you guys an example of how that looks like. Let's take the limit as h goes to 0 of the function I had written above. So f of 1 plus h minus f of 1 over h. And realize here, calculus tells me, hey, here's this, I'm gonna let h go as close to 0, and here's a way you can compute it so that when we know that h is as close as 0 as we can, basically almost little to no difference between the data points, we're able to find the instantaneous rate of change. And this is what we'll be exploring throughout this unit and our next unit. I hope this made sense, and see you in the next video.